So of course, session analysis is key to the use of GIS. We know already that GIS basically arrange data in layers form, all right, and each layer has its own theme, all right, or we call it a thematic map, all right, that represent a single sort of entity. And then this is actually how we can utilize all the data gathered, all right, from the sources to perform, sort of many tasks, right? And of course, GIS have the ability, depending on the proprietary software, right, to perform tasks from the data that are stored in the database. Okay, so database is very important. In fact, it takes about more than 50% time consumed in preparation of a project in a database, because in a GIS, because without data, it can go further in terms of getting tasks or getting what the user requires or what the user demand for in terms of the analysis. And of course, when we have everything about computer, we simply transform data into information. And of course, it involves a lot of processing functions and then combining spatial and attributes database. All right. And then, of course, this information can be used for many decision makings. In fact, sometimes it helps users, okay, to perform or to give an indication of certain things in a quick manner, in a very fast manner, all right, by the click of a computer or with certain functions that a GIS capable of. All right, GIS representation in computer. Of course, when we want to prepare a GIS project by using certain data from various sources, right? So we need to know what kind of data to be put in the system, and then what sort of analysis we want the data to perform, or we want the data to show, right? Well, from the user sort of requirement. And of course, data can be selected according to geographical location, because spatial is about map, right? Or it can also selected from the teams, from the individual entities that a user deem what we call necessary for the use of the data or the function of the analysis. And of course, for us in Raster, right, we have many diverse sort of activities or services involved in real estate. Like the one I gave you in the questions, it's all about valuation. It's all about estate agencies, developers, maybe, or property management, which are these are four sort of core in real estate aspects. So when we want to do a project on GIS, we need to confirm which segment we want to go for. Let's say we want to become what we call, or to set up, let's say an estate agent office, for example. So what are the required data relevant or related to an estate agency, right? It could be, the listings is very important, right? The properties, okay, and then you need to have listing also not only on the properties, but you need to have listings on the buyers, the sellers, right? Prospective buyers and sellers. You need to have some data about the office setup, all right? The salesperson, the REN, negotiators, for example, and then you also have your real estate agent that has been, sort of certified, qualified as an agent, REA, they call it, right, registered as an agent. And then all other aspect about, selling, about, negotiating, maybe. So that's the kind of data that we want to, put together in the form of database structure, and then that structure, transform or convert into a computer systems. So that's how it works, because we need to prepare what we call conceptually, and then we transform that concept into the computer setting. I think GIS plays a lot of computing techniques, basically, in order for us to really get to know more about its functionalities. But of course, as a user, we simply, when we acquire the software, and then we simply have data on it, and then we simply add on the data and then perform sort of tasks that are related to the data only. But of course, for GIS developers or like, programmers, for example, or computer persons who develop the software, they can do as many things as possible because they know about technicalities of programming, for example, because you need to program, right, the software to perform tasks. But for user, we simply click here and then we get the job done, right? So basically, there are distinction between aspects that a user can perform and aspect that a developer, a computer developer can prepare for in terms of the analysis, right? So what is special analysis? Of course, special analysis is simply a set of methods, okay, to carry out special operations. There are different sort of naming, okay, of those functions that special analysis can do, all right? So basically, in any computing technology, if it's involve a lot of data, so we have the input, which is the data, and then what we want is the output from the data, right? So in between, there should be some sort of what we call function. In this case, it is actually special operations. Or in other words, we can also have input, process, output. So this is actually the process part of the analysis. So you came across these terms, IPO, right? They call it input, process, and output. A lot of it was, used in computing sort of terminologies. Right? All things that are associated to data as well. And of course, the aims of the analysis is to find out special relationship patterns and trends. Okay, of course, we want to find out from the data about how one entity related to another, for example. So you have different layers of information. For example, you want to know which particular location, sort of close or near to the other location, for example, all right? Or you want to know the coverage area of a place, or you want to know how many people or how many customers are within certain radius. So that's kind of, examples of relationships, patterns, and trends, right? And of course, the results can be used to solve what we call the special problems or any query or any warranted issues that the user deem important for the analysis, right? And of course, the capabilities of GIS can go beyond mapping because it simply transforms whatever data we have into a new set of data, okay, by way of showing, sort of different visualizations of data, because each layers of information, maybe not all, you can select or deselect, okay, any kind of layers in that map, for example, to show only certain aspect of the data or of the result that we require only, all right? Components of special analysis, okay, these are quite general, okay, we can explore, okay, which is actually finding interesting patterns or trends and relationships, or we can use modeling, okay. Of course, modeling needs to couple with some sort of mathematical formula, for example, like statistics, or you want to couple with other types of software if you want to show some kind of trend surface, right, in 3D way, for example. And of course, the good thing about computer, it can simply visualize on screen or it can be printed out, right, the result. So let's look at this example here. Just imagine that each X, Y, and Z, or Z, all right, is what we call a different entity. And of course, X is the same entity, Y is of course the same entity, and then Z is actually the same entities of geographical object. All right, just imagine anything. It can be points. Okay, X could be point. Let's say a bus stand, for example, or it can be fire hydrant, or it can be a particular location, right? On an area or location. And Y, it could be something else. It could be a polygon of something, okay, or of a theme on geography. And Z also could be something else. It could be an ocean, a lake, for example, a pond or whatnot, right? So we have three sets of entities, X, Y, and Z. So we want to know, its sort of relationships, or we want to further explore, all right, how X and Y related to each other, or how X and Z related to each other, right? So basically, we can simply query, or ask the systems, the GIS. Okay, for example, does feature X, okay, occurs in a pattern? All right, if you look at this picture here, okay, of course it does, right? If you look at, from your eyes, okay, from your bare eyes, and of course in computing, if you simply put such question, of course it will simply show you the result, all right, without X and also without Y and Z. And of course X, Y is actually occurring in a pattern, all right. So basically it actually goes from northwest, let's say, all right, to the southeast, for example, all right, in this case, right? So it simply go in a line, okay? It does not necessarily a straight line, right? It can be a connecting between X, let's say X1, X2, and X3 in the form of linear functions, right? Similarly, we can also ask, is there a relationship between X and Y? Okay, what sort of pattern do you see from between X and Y in this case? Just look at X and Y. What do you see?
Always adjacent to one another.
Okay, right. They are simply close to each other. Okay, it might not be adjacent. I'm not sure, but adjacent means it should touch, right? The borders, the boundaries, adjacent, next to each other. But of course, it's next to each other, but it's simply close to each other. Okay, so basically, Y is always close to X. Okay, this is actually how GIS translate what we call the query into answers. All right, and look at number one here. It always shows a bit of direction because each data, each spatial data is what we call georeference. That each data has its own XY coordinate. All right, so basically it is in real what we call coordinate systems, okay, of the world, for example, right? So each spatial entity here has its own XY coordinate. That's why it can tell us that line X occurs from, let's say, northwest and then cross to southeast in this case, for example. And then number three, what are the spatial and pattern analysis exist? Okay, of course, we can simply look at this data, and then, for example, feature X always near to the boundaries, for example, okay, here and here, and its sizes also, its size increase from west to east. You see from the far west, for example, or far left, it's a bit small, okay, and then it simply grow, okay, slightly bigger and bigger, and to the biggest one to the east. So it moved, let's say the size increase from west to the east. That's the kind of what we call pattern that we are looking for, or that we can sort of describe, right, from what we call the analysis of spatial, for example. Okay, there are at least 5 types of spatial functions or spatial analysis that a GIS can perform, and these 5 are the most basic ones. I'm sure all or most what we call GIS softwares have the capability to conduct or to carry out all the first 5 functions here. And of course, number 6 is quite special. It could be, occurred, or it could be existed only on high sort of level of software that can perform, or that can couple, or that can perform statistical computation and then couple with other sort of software, okay, or other advanced functionalities, like say spatial modeling or geostatistical. This is actually a statistic functions, all right, but it's more on geography statistical. Okay? It's quite advanced when you geostatistical analysis. The statistics comes from the map, not from the numbers that we used to do, or that we used to to have access to. So of course, if you want to go to more advanced types of statistics, we can simply go on geostatistical function. Okay, but anyway, we will focus on the first 5. All right. To be honest, I'm quite disappointed because I couldn't show you from the actual software that the GIS can perform this analysis because of obviously I couldn't get also a license, right? Because it's only in the lab. Okay, special query. Okay, queries or simply questions. All right. You can. I mean, you ask the systems to get or to retrieve whatever information from the special as well as from the database. All right. Remember, a GIS component has two: data, special and non-special database. Right. So we can simply query whatever information from the map. Okay, as well as from its database, okay, the tabular ones, right? And of course, the computer systems works by way of a logical, I would say logical conditions, okay, and mostly the underlying backbones, all right, of this logical condition is mostly on, algebra or using some sort of Boolean operators. Okay, remember when you search information from the library for books, right? For example, you are actually assessing the Boolean operators, or you can also look at logical condition. Let's say you want to search for real estate, you can type in real plus, all right, estate. Okay, so it will simply retrieve any words or any, let's say, articles relevant to real and estate, all right, together. Or you can simply type real and estate. Okay, or the most easier one, you simply what, quote unquote, right? Quote real estate and the unquote real estate. So whatever information it will respond to will have this real estate sort of words in there. So this one is quite helpful in for you to do, your thesis later on, right? You want to find some sort of literature. So basically, I'm sure you have really mastered, okay, on the searching function, because this is what the library has taught you, right? In terms of finding information from the database. But here it also employs the similar way, okay, of asking the computer by using sort of these logical conditions or Boolean operators, right? And of course, this example shows you the result, all right, of the sort of query. Okay, let's say you want to get information, let's say from feature one to another feature here. Okay, and then you want to have two features that is combined together, or they are combined together, and then you put the word and, all right, here, or you can simply put the plus sign, right? So anything or any information that the computer will give you should contain both objects. So of course, the second object has a circle in it. So anything outside of the circle will not be retrieved by the systems. Okay, because we only want, we must include what we call the circle as well as the other object, which have information in the circle and information outside the circle as well. But of course, the desired result or the expected result is anything that is included in the circle. All right. And then actually there's a sort of common understanding here in terms of asking the systems to get whatever information the user wants, right? Um, because in this way we can simply manipulate any kind of information that best suit to the query or to the questions that the user wants, right? And the most important thing about special information, because when we draw a map, right, we have identified its what we call attributes of the map, or its metadata, right, of the map, or sometimes we call it a characteristic of the map, such as its length. Okay, if you draw a line, okay, let's say a line here, it has a length, okay, from start to end. What is the measurement of the length, for example? Or if we draw, let's say, a polygon, it also will give you a bit of information on the area or size of the object. Okay, and by the way, the basic principle of GIS, each point has what we call the XY coordinate, right? So that's why we can simply measure the sort of the real size of the, let's say, a polygon, okay, on a map, all right, because it will simply retrieve or bring back the information that is the actual sort of map, see the actual measurement area or length, okay, of a specific entities from the spatial information, right? Basically, remember we have two ways of asking the data, one through map, okay, the other one from the database, okay. So from the map or from the special query, the user will simply employ what we call this the map, okay, as a query tool to obtain list of map elements that meet a particular specific criteria, right? Have you heard about the word SQL? Do you know what is SQL? SQL, eh?
No.
I put here SQL. SQL is actually structured query language. SQL is structured query language. Is mostly used in many GIS functions for spatial query as well as attribute query. So SQL basically have certain conditions or certain what we call feature that the user wants to simply get results on. Okay, I will show you some example later on conceptually, right? But in GIS, for special query, they have three categories. One is to ask direction. Second, you can ask distance, and then three is mostly to do with math. Now, the only like topology, because topology basically, you know, asks you about mostly about the features of the object, right? Because geographic spatial map, right? Okay, basically based on specific geometric, what we call feature, points, lines, as well as a polygon. So direction questions, we can ask information about, let's say, orientation of features on a map. Simply, we can just imagine it, for example, from the map itself, right? We can simply put, I just said some SQL functions in the systems, and then it actually will simply perform this query and then provide the result, okay, of the queries. Let's say we want to ask what neighborhoods are west of central KL. Okay, just imagine a map, all right? Okay, a column map, for example, and then we know the location of central KL, and then of course we need to identify the north, okay, location, the northing sign, right? Because the north will indicate where the exact position of central KL in relation to the world map, for example, right? So the system will simply provide us with any neighborhoods in our database, okay, that are located west of, let's say, central Kuala Lumpur, all right? Similarly, we can also ask which cities are north of 40 degrees latitude. Because of the beauty about GIS, it has what we call relevant coordinate attached to it, okay, on the map. So it will simply provide you with the answers easily, okay. And then additional questions ask you mostly about, you know, proximity, about, you know, a length from one place to another. We can ask about how far is it KL from JB, for example, or how many cities are within X distance of an earthquake. Okay, this is actually a real example taken from GIS software. And then, of course, topology questions related mostly about the features, okay, of these objects, points, lines, as well as polygon. Let's say, do they share boundaries? Remember, we can have, for example, in this, I just simply can show you just a quick example, yeah. Okay, just imagine this is actually an object. Okay, an object. All right. So, and then we create another object, for example. Okay, another object. Let's say if the object is, let's say, touch. Okay, the boundaries. So the system can ask, does the model, the data, okay, the spatial data, do they share boundaries? Okay, and then it will show you the result. All right. Or do they cross each other? okay, or overlap. Okay, we call it overlap. Okay, overlap each other. Is one contained within another. For example, a small area, okay, inside the bigger one, right? So it's one contained within another. So this is actually, some sort of ways GIS interact with the data, right? And then there are many more basically. Okay, some questions, just a quick one. Okay, okay, this is basically taken from the website, right? From a particular GIS software, and then we have this sort of order for us to simply identify what type of features that we want the GIS maps to show us, right? For example, in this example, it wants basically it simply wants an information about I think it's about what is EQ? 2009 EQ or something. Some particular objects of the geography that are within a distance of certain counties, for example. So and then the red dots, all right, are the sort of the results, okay, of the systems of the output, okay, from the query. So it simply shows you this particular object are within a distance of the countries. Is it country? No, distance of here a buffer, all right, of 1 mile. Sorry, of 1 mile, and then it showed you the result showed you in this layer. Okay, countries layer. These are the countries layers, and then the query simply asks you this feature that are within distance of what we call 1 mile, right, of the selected what we call feature of the geography of the object. And then probably on another example, the system could ask, the user could ask the system about what is the average household income in 2010, okay, by looking at this what we call matrix, all right, or at this what we call ranges. Let's say income of 60,000 and below and up to 135,000 and above. And then it can simply show us which particular area, let's say in a particular town or in a particular city, about the household income, okay, of the occupants or of the residents in a particular location. Of course, remember, before we get to this result, right, the main thing about it, we need to put in data in the database. And then that data associate to the aspect of the map. That's why it can perform this task, because when we work on the map, we also work on the database, tabular database that are sort of linked to the map. So if we have thousands of data, this is actually the best that we can perform for. Of course, we cannot perform more function when we only have, let's say, only 10 sets or 20 sets or 30 sets of data, because it won't tell us about the generalization abilities, or in fact, it won't give us a clear picture, right? Or thorough pictures about, let's say, average household income in a particular area, all right? Attributes query, okay, asks information from the table itself, all right? Just now, the system asks from the map information, okay? And now the system can also ask from the table information, okay? And then this table also can be plotted or can be linked to the map as well. So basically, in either way, if you ask a map or if you ask table database, both also can correspond to each other. Let's say in this case, if you ask attributes information, it also can show you the result on the map as well. Similarly, if you ask the system on the map, and this map also has associated table database as a result, okay, of this query as well. So basically, both special and attributes are linked to each other, all right? And of course, we can use similar functions of the query, either as Boolean or either as what we call this geometric plus minus sign and so on and so forth. Okay, this is actually an example of attribute query. Remember I said you about the SQL, right? And then this is actually how it looks like. We have name is actually the entity, okay? Sorry, is the title, right, of the table, okay? And then it has what we call certain what we call titles, name, state name. I mean in the columns, right? For each column, population 2000, population 29, population, let's say per square meters, population per square meters, and so on, so forth. All right. So these are some of the what we call selection or some sort of selection by attributes in one of the softwares, and then we simply have what we call these are the conditions. All right. That represent what we call the query language, right? So basically, if we want to get to know, let's say state names equals to California, okay? We use the word equal here, all right? So state name equals to California, right? And then where we want to put the result, okay? In here, it simply say create a new selection, meaning to say that it comes up as fresh result, all right? Not as part of the existing maps, all right? So basically you want a different map, okay? From the entire map, okay? You only want to show name or show California only, let's say from the entire US states, okay? And you can also probe further to ask more information about, let's say, California. For example, you can ask population in 2000 and population in 2009, all right, by having the structured query language. All right? And in other softwares, it also can use different terminologies. In this software, in particular one, ArcGIS, is use the word select, but in MyInfo, it can use the word find, okay, F-I-N-D, right? Find. So anything that represent a selection of query functions, all right, can be made a similar way, all right? They also employs what we call this structured query language. It is actually a computing terms, basically, used in computers to perform this selection of query function, right? And probably these are the desired result, all right, in the form of tables. Let's say we have thousands of data, so that result probably only a couple of data, maybe 10 or 20, lines of data only, rather than showing the whole lot, right? We can simply pick and select the desired one. So basically, that is the beauty of GIS, and basically selection of query function is the most basic and in the most what we call use functions in a GIS, all right, for a normal user. And of course, the beauty of GIS, it has a geometrical features, okay? So we can simply also do measurement, all right? And then of course, measurement relates to each types of entities, points, line, as well as polygon, all right? If we were to ask points, of course, we cannot ask distance, right? Because points only has a single location, right? And then probably you can ask the line to measure from one point to another. Similarly, you can also calculate a parameter and area or size of the, let's say, a polygon object, right? So measuring distance, there are two sort of terms or two types of distance measurement. One is simple distance, and one is with a functional distance that has something, some what we call frictions or some barriers along the way, right? And of course, when we want to measure distance, we can employ, in maths, right? You use Pythagoras, right? Pythagoras theorem to calculate from distance from point A to point B, right? X2 minus X1. I think it has square root whatnot, right? That kind of thing. So that is actually the work of the mathematics behind the formula. And then for Manhattan distance, is basically used to calculate the distance along the raster cell side, because raster cell is actually, each cell is look like a square, right? So we cannot simply cross the square. You need to go along the boundaries of the square. But this is actually another aspect of GIS Manhattan way, okay, of calculation, right? We don't really want to know more about that. We just want to know, all right, vector can use simple and function distance, and for raster-based map or raster-based model of GIS can use Manhattan distance function. All right, Manhattan distance go around a cell. All right, remember we have a raster-based image from a cell. All right, let's say this one. Okay, a cell. Each cell is a square box, right? So that's why it needs to go around it, okay, rather than normal, Pythagoras theorem. We can simply go across it, okay, x to y, like here, right, x to y. So you nothing simply plus this and that, right, using a Pythagoras theorem to get this length or xy length, for example. And then we could also calculate a perimeter and area of the spatial object, right? And then for distance, we have, I said just now, straight line distance. Okay, basically you want to measure location from, let's say, Alostar to Kuala Lumpur. You simply go straight line distance, or you can measure along a route, right? Along route of the feature. Okay, of course, when we go ahead to measure the straight line distance, it will be simply what, shorter. Okay, because we assume it is actually straight line, right, from B to A. Compared to if we simply follow the, let's say, North-South Highway or North-South Expressway, right? So it could be much, what we call further distance, because we need to know about the, the roads are not really straight up, right? And then there are some friction in terms of movement, okay, of traffic and so on and so forth. I mean, straight line distance, just imagine an aeroplane fly from B to A. Okay, let's say in a straight line distance, okay, straight away, okay. Functional distance takes into account what we call the barrier, right? Let's say this is actually the barrier you want to measure from A to B, okay, and it simply can deviate the barrier, okay, along the way. Let's say instead of calculate a straight line distance from A to B, then you need to take into account this barrier, and then instead of going straight, you need to deviate a little bit, all right, because you want to get access to B. And probably this is how it looks like in our normal, what we call day-to-day operation, right? Because in order for us to get point A to point B, we of course, in terms of, if you look from the air, you can draw a line, just a straight line. But if you are on the road, okay, on the actual road, okay, you cannot go straight line because we have a lot of establishments, right? A lot of improvements, a lot of buildings, okay, along the way, and then follow the route or the road that leads from point A to point B, right? Okay, another bit to aspect about GIS spatial analysis is overlay function, all right? And then overlay is a technique where we can simply have certain selection of teams, okay, on the map, and then it basically will transform into another set of information, okay, by overlaying it, all right? Because of the arrangement of the spatial map, okay, in the form of layers, we can select all of the layers, or we can select only a few layers. And then let's say you select layer 5, 4, and 3, and then when you overlay them to each other, it will simply give you a different sets of look or different sets of result, all right? Depending on whatever information you have from each team, okay? From each layers, right, of the map, of the team, of the thematic map, all right? So basically, the main function for overlay is to create new layers, all right? to give you or to provide you with new kinds of information. I have an example here. Okay, for example, conceptually, right? We have these two layers, all right, that needs to be overlaid, all right, and then probably the first layer is represented by one team, right? And then the second layer actually is another team. Okay, let's say land use as well as the what we call the boundaries, okay, of the land, right, of the area. Okay, land use, we have one and two land uses, and then we have a boundaries map, okay, of a similar what we call map or similar special feature. So when we overlay the map, okay, it will give a new, it will give result, and that will give you what we call a new layer that composed of, the land use map as well as the boundary or the, let's say, the district it actually belongs to, right? So instead of you have two entities only, when you overlay, it gives you, let's say, four geographical entities in there. All right, it could be land use one, okay, occurred in 1 and 3, right? If you overlay this map, right? Let's say land use one is, let's say, forest, for example, and the other one is just a field, for example, all right? And then number two could be something else, right? So basically, the point is you overlay them so it will give you a new result. It can help users to make a better decision with what we call specific result of the overlaying, rather than looking at two sort of separate layers. So it can provide you with more insights into, the location or into information about a particular spatial feature. Okay, in this case. In Raster case, for example, let's say we have three individual or three teams or three objects of spatial. One is actually roads, all right, and roads normally represented by lines. Okay, you see all the red, of all the white lines here that represent roads in a neighborhood, and then you can have another layer about a parcel, a lot parcel, okay, or land lot, right? These are all the parcel. Okay, remember each special object here has similar what we call as similar boundaries. Okay, so we can control the alignment, okay, of each of the layers. And then probably the third one represented by houses. All right. So if we overlay all three, all right, it will give us the entire layout, okay, of, let's say, a neighborhood or a specific neighborhood, all right? And then with this information, with this new layer, all right, when we overlay all three layers, okay, it can provide us with, the shape or with the layout, okay, of a neighborhood. It provides us the specific, situation or fixed conditions, all right, where the house should match with the parcel lot, all right. Let's say you want to do analysis on houses and also the parcel or the land parcel, right? So we can overlay these two, okay, without the lines as well, all right. And then we can simply do whatever analysis we want from this new sort of new layer or new teams, okay, that combine all the three layers of information, right? In raster is all about specific cell, all right? Of course, when we overlay, let's say a raster based map, okay, from one layer to another layer, it will combine, the feature to the next feature, okay, of the layer. Okay, let's say we combine layer A and layer B, so the result give you for each of the cell grid or grid cell, right? Let's say A2, and then you get A2, and then A1 here, and then you get also sorry, B1. Look at the position B1, then you get this new grid as B1. Okay, probably because of the raster represented by pictures. Okay, let's say A has its own what we call density, all right, of the picture of the image, and 2 also has its own density. So you combine those two, maybe you get a new sets of density in terms of the colors, okay, or the coloration, all right. Or in terms of real life, for example, um, probably this is actually the soil name, all right, A and B, right? And then this is actually the types of area that it represents. 1 is forest, 2 is urban area, and 3 is sort of farm. So let's say you combine these two, so you get A1, you have forest, okay, forest, and the type is mostly is event loam, for example, okay, the type of soil. In this case, okay, right, in this example. So basically, whatever corresponds to the spatial image in raster also represent the same thing in the attribute or in the tabular database. Okay, that's how it works in GIS. The other function is a buffer, all right, buffer function. So buffer simply just some kind of width or zone, right, drawn from a specific point, okay, of the map, all right, and then we can actually buffer each and special entities, points, lines, as well as the polygon, all right. So let's say buffer is important in terms of when we want to analyze a specific location, and we want to know, let's say, a catchment area of that specific location. All right, let's say you want to find a location. Okay, in real estate, you want to find the best location for you to, let's say, develop. Okay, or for you to create or build, let's say, a township. All right, or simply a mall, for example. So that particular location of the mall, right, needs to have what people or consumers or customers, right, around the areas, surrounding areas. So we can create a buffer from that point of that location of the proposed mall, for example, or the proposed development, and then you can actually go by radius. Okay, let's say 5 kilometers, 10 kilometers, and so on and so forth. All right, so it will create all the catchment areas, and provided the map has all the data about customers, and then it will show you how many customers or how many people or how many populations are within certain radius, distant radius. All right, for example, within what 2 miles, 2 kilometers, 5 kilometers, 10 kilometers, and so on, so forth, so that a developer can, project or can design a proper scale of a mall, okay, in terms of the and what kind of mall they want to simply build, right? And probably for rivers, it's also important to see the flow of the water in the rivers and whether the water can outflow right to the entire to the adjacent or to the boundaries area, all right, of the rivers, for example. So we can draw a buffer up to certain radius as well, okay, around the lines, okay, of the river, to see if most likely if there is a heavy rain, for example, so that river could only outflow up to certain distance, all right? It may not outflow to the rest of the area, for example. So we know the strength of the river, as well as, let's say, we can decide whether this river needs to be what? Deepen up, okay, you need to dig more to make it much deeper, for example, so that to avoid flooding, all right, from the run of the water, okay, of the river. Now, especially in Malaysia, right, we have a monsoon season right now. So most likely this is what they need to do, right? To create or to analyze how much water that the river can spill out, all right, to the surrounding areas. And similarly, you can also buffer an object of a polygon, all right? It works similar way, right? So you can basically to create individual buffers, and then this new buffer, all right, can be informed or can be a tool to inform the user of certain sort of results, okay, right? Like what the user desired. This is how it looks like. It's supposed to be looks like, all right. Buffer distance, all right. And then when you buffer a special object, it simply follows the boundaries, okay, or the shape of the original object, right? So if you draw out a buffer, let's say 5 kilometers, right, from the boundaries of the picture, so this is actually what it should look like in terms of the result, okay, of systems. So it simply follow through the shapes, okay, more or less, right, of the buffer distance, all right. Similarly, in this case, if you want to buffer a point, let's say area within 1 kilometer to a hospital, all right. This is actually hospital, and then you want to know the surrounding area, okay, in of 1 kilometer from the point of the hospital. Or you can simply buffer a line, okay, area within 100 meters to a road, for example, so that the government can, provide sort of road reserves, right, around the area, so that nobody can simply, develop that land bordering the certain types of roads, for example. And then you can simply buffering an area, for example, 50 meters to a building, right, probably to provide certain what we call open area. All right. So basically, within 50 meters surrounding the building, okay, it could be just an access, or it just could be just a walking path, for example, from the building. So this simply helps in terms of designing or creating, all right, the actual what we call feature on the actual sort of location, right? Okay, an example in terms of real estate, let's say we have our subject property, okay, and we buffer our subject property to find, let's say, parcels or probably a comparables, right, within 100 feet of the subject property. So anything that is close to 100 feet to the subject property is being buffered, right? It's being selected, okay, and then instead of looking at each individual parcel around the area, okay, so we can get only a handful or some of the parcel that are close to our subject property. Okay, simply let's say, for example, here, if you want to buffer an area from a bus stop, for example, it simply what provide you with the length of coverage, okay, within a certain distance from the point that we are buffering on. Okay, so basically it will tells us, much about that information only. Okay, let's say within this circle, okay, rather than looking at the entire sort of map, right? So probably users are only attracted to know more about the closer area, okay, rather than a bigger area. Okay, the beauty thing about this is actually each special object has its own corresponding table, all right, or database. So that database can tell us much more about the information of the map as well. Okay, another one is actually classification. All right, classification is used to identify a set of characteristics to group together object. All right, it's simply more or less it works similar to overlay. All right, because when we do classification, we also need to overlay as a result of the overlay. Right. For example, when we overlay two objects or two feature or two special teams, all right, 1 and 2, right, and then this is actually the result, all right, and then we can classify or reclassify the result into a new sets of information, right? Let's say when we do that overlay just now, okay, it gives us these 4, let's say, component, okay, of the map, and then we can simply reclassify them into another new sort of theme, right? Of course, when we look at here, of course, in terms of land use, right, although it's residential and industrial, but this belongs to a category of urban. Okay, so we can simply combine these two to become, when we do classification or reclassification, that will result as what we call the entire what we call urban area, right? Similar to the other sort of the other sets of data on rural forest as well as rural agriculture. So it works, front to end and end to front. When you do overlay, you are actually doing this, right? This to this. But when you classify, you are actually doing the other way around, all right? So basically, you can couple overlay and classification together in, let's say, in an operation, right? Just a simple example of a map showing classification of buildings according to age, and of course it gives you this sort of colors to indicate the difference sort of among the buildings that have different age, right? For example, let's say the off-white colors is before 1990s. Okay, only 3 properties or 3 locations here, for example. And then the blue colored, the age of building is between from 2000 to 2009. All right, and then the rest showed you different sort of sets of age of the building as well. This is a general way of what we call GIS classification do. Is simply reclassify the feature into a new set of feature. All right. And then most likely, when we want to visualize information from the map, we can actually show it by way of a thematic map, right? Because in each layers of map already has its own theme. Okay, when we do, let's say overlay or classification, we can add what the result give us is actually a new map, and then that new map can be saved as a new theme. All right, and then of course themes represent data with many elements of the map, like colors, patterns, symbol, grids, also chart, and so on and so forth, right? And these are some of the elements of a map in a normal map as well. All right, range data, for example, you can show the result in the form of range, let's say population density by state in Peninsular Malaysia, and of course it shows us in different variation of colors to indicate the depthness, right, of the density. For example, the most darkest colors, right, has a density of 1,501 person per kilometer, per square kilometers. Okay, probably it only occurs in the Klang Valley, yeah, okay, or Kuala Lumpur for that matter, right? And probably some parts of Penang, okay, the island, right? And probably the least density places or states in Malaysia, for example, according to this data, which has less than 100 persons per square kilometers, Kelantan, Terengganu, as well as Pahang. Okay, of course, because of probably the nature of the countries, right? Pahang, a lot of forests there, a lot of hills and mountains, right? And Terengganu, similarly, shares some kind of this, that Banjaran Sriwangsa kind of thing. So you can develop, right, much of the area, okay, to put, to have more people in that particular area. And we can also have range data, all right, map, let's say states by population in 1990, 5.5 million to 30 million, all right, where is the states that have this kind of population? Probably in many sort of east side of the states, okay, and as well as California, if you look at this map, and Texas, for example, Miami, probably, right? So these are the states that have the most sort of populations, okay, in the US, for example. And then there is also what we call a gradiated symbol, shows us varying in size according to value, and probably each size or each sort of dot, right, has a value in it, and the more bigger the size, indicate the higher sort of values in the circle. Right, for example, this map shows us the population of city, and then we know from looking at this map, which states in the US, for example, has the highest population, all right? Or which state capitals in the US has the most population in the country, all right? And then it also can show us by different symbology, like human, a person, yeah, rather than a dot here, all right? Similar way, and each size, okay, of the dot represent certain values, all right? Population of urban population in the states, right? Let's say the biggest one is 28 million, right? So probably California has the most urban population rather than the other states, all right, of the US, for example. And then, of course, the other common ones, like statistical, also can show us, when you do your descriptive analysis, this is actually what's shown, right, as the result of your statistics. Bar chart, pie chart, and then bar chart also can be coupled onto the map themselves, all right. Here shows us a bar chart of states with, let's say, the highest rural population over urban population, the green one, and the entire sort of population when we combine between rural and urban location as well, all right. So it indicates, probably we have the data, all right, from the database, and then it will fit the data into the results, okay, of the map. So the good thing about GIS is you can plot, or you can show your bar chart or pie chart onto the map itself, all right. So we know straight away, or we can simply visualize, all right. Let's say Michigan has, this kind of amount of population of urban as well as rural, and population in the 1990, for example, all right. So from here also we can simply generalize that, probably New York, Pennsylvania, okay, has the higher population, right? Or probably you want to look at the highest population of urban, probably in the New York states, okay, rather than the other states of the US, okay, by looking at the size, okay, of this bar chart, for example. Bar chart also, similar way, we can also perform or replace bar chart to become what we call a pie chart. Okay, the much or the more bigger chart, okay, shows us the higher sort of density, okay, of the population, let's say in this case, right? And then of course it can show us with other types of map, dot density by way of single dots, okay, and then that dots represent what we call certain values. Let's say in this case, one dot represent by 25,000, okay, population. Here is, in this example, it gives us the population of Asian, all right, in the United States, for example. So one dot equals to 25,000. So you know that 25,000 represented by one dot, and then the more dots that the map shows, right, in each particular state, show us what we call the more, let's say, people, right, in that particular state. And here, for example, Asian is mostly located in California, okay, and some, let's say, is mostly in New York as well. And these are the two states that have, mostly population of Asian people, okay, in the US, for example. Or we can simply put result onto what we call this individual values map. And individual value give us, sort of an individual color for each particular result. Let's say we have 50 states in the US, and then it will show a different coloration of the result for each state, okay, in the US, right? So these are some of the information or some of the result that we can get from what we call GIS special query, okay? So basically, I have ended my lecture, okay, from the schematic maps. Do you have any questions or any concerns about this lecture on the topics?
Still okay.
Okay. All right, then don't worry about much about it because we can't see the actual work in play. Anyway, you just think, just try to sort of when you read, right, or when you try to understand things, you need to visualize because GIS is mostly about uh, visualization, visualizing the actual object, right? Because it involves geography, it involves maps, right? So we need to do a bit of visualization. Okay, to move forward, I I will create some sort of task for you related to this topic, yeah, and probably some other previous topics that you can easily do. Okay, it's more like a task that you need to sort of follow through some certain guidelines, and then that can be sort of the test, okay, for these topics on GIS. All right, I will post that question probably starting from next Tuesday. Okay, next Tuesday, early morning Tuesday, and then you will need to do it. Use that the whole 12 week 12 Tuesday and Thursday, or in any times in between, right? To do the test and then submit to me by end of Friday maybe. Okay, end of New Year Day, boleh boleh ke?
Boleh.
Boleh okay, don't worry about that. It's just a small exercise for you to do. It's more on understanding aspect of it, right? Just a simple query, just a simple questions I will put on next week, all right, for test. And then for your tutorial this week, okay, please continue on with the database, okay, in a group work, all right, and submit to me. I will extend the submission dates, right, the due date by end of this week as well, so that you can utilize that Thursday to do the to have it submitted